Welcome to This Explainer. Today, we're diving into how AI agents are finally moving beyond basic amnesia to achieve true long-term reasoning. If you've been building or working with AI lately, you already know that keeping an agent on track over a really long interaction, it's honestly one of the absolute hardest challenges we're facing right now. I mean, we've literally all seen it, right? A customer service bot absolutely nails the first 4 messages perfectly. It gets the order number, confirms the name, updates the shipping details, and then suddenly, it just completely loses its mind and context by message 5. It starts asking for the exact information you literally just provided. So why does this happen? To figure out how we fix this, we're going on a quick 6-part journey. We'll cover 1. Why AI agents forget, 2. The 4 types of AI memory, 3. Hierarchical OS memory, 4. Knowledge graphs, 5. Active dreaming, and 6. Strategic forgetting. All right, section 1. Why AI agents forget. You see, the issue isn't just that the underlying models are somehow broken. It's that our default storage mechanisms are fundamentally flawed for long-term agentic workflows. Think about it. When we just dump everything into a flat vector database, we trigger 4 specific, completely predictable failures. First up is context poisoning. That's where the agent stores and then actually reinforces its own hallucinations. Yikes. Next, we have context distraction, where the really critical data gets buried under a mountain of semantically similar but totally irrelevant noise. Then there's context clash, right? That's where contradictory facts, like say an old address and a new address, are loaded at the exact same time. And finally, work duplication, where multiple agents just blindly repeat the exact same tasks because they completely lack a shared state. So to actually solve these failures, we really have to split AI memory into 2 completely distinct categories. First, there's parametric memory. This is the stuff baked directly into the model's weights during training or fine-tuning. It's incredibly powerful, for sure, but it's totally opaque and wildly expensive to update. And then there's contextual memory. This is external, explicit, and queryable. For the rest of this explainer, we are going to be focusing entirely on improving that contextual memory to give these agents an unbounded, dynamically updatable history. Moving right along to section 2, 4 types of AI memory. Honestly, treating all memory as identical is the root cause of so many production failures, so we really need to categorize it properly. It is absolutely fascinating how closely we can map human cognition directly onto AI architecture here. Look at working memory. That acts as the fast but super limited LLM context window. It's essentially your active workspace. Then, episodic memory tracks specific past experiences, like a conversation you had yesterday. Semantic memory is the persistent knowledge base of world facts, like standard medical protocols. And finally, procedural memory. This encodes learned skills and validated action sequences, which is a real game changer because it allows the agent to execute complex tasks without having to reason from scratch every single time. Okay, section 3, hierarchical OS memory. Because let's be real, when you've got millions of episodic and semantic memories, a flat search is just going to completely drown the agent in noise. The best way to think of this solution is exactly like a computer's operating system. Frameworks out there like MemGPT use this brilliant tiered model. The LLM's context window, that acts just like RAM. It holds the core memory, which is always fast and right there when you need it. Meanwhile, the external memory acts more like a hard drive. The agent actively uses explicit function calls to basically page information into the context window only when it's actually needed, and then it just evicts it when it's done. Other systems like MemoryOS expand this whole concept into short-term, mid-term, and long-term personal memory tiers to summarize and route topics absolutely flawlessly. And here is the kicker. By shifting to this hierarchical management, token costs for agentic workflows get slashed by over 90%. I mean, that is huge. You save a ton of money, you significantly reduce latency, and, somewhat paradoxically, you drastically improve contextual relevance. Why? Because the agent isn't constantly getting distracted by irrelevant data. Let's jump to section 4, knowledge graphs. Vector similarity is really great for general concepts, but when it comes down to it, fuzzy semantic search just isn't exact enough for real structural truth. Let's apply this to a high-stakes scenario to really see why this matters. Imagine a medical AI using a temporal knowledge graph. It doesn't just pull up documents with similar-sounding words. No, it performs exact multi-hop reasoning. It sees, okay, the patient has hypertension and identifies drug X as a treatment. But then, crucially, it maps the relationship showing that drug X is contraindicated with drug Z, which the patient happens to be taking. By traversing these explicit edges, it safely pivots to recommend an alternative, drug W. A standard vector database, it could so easily miss that lethal drug interaction. The ultimate takeaway here is really all about explainability. In highly regulated domains, think medicine, law, finance, your agent absolutely must be able to explain the exact factual chain of reasoning behind its decisions. Knowledge graphs give you that exact explainability. They tell you precisely why a decision was made by following verifiable nodes and edges, rather than just crossing your fingers and relying on some mathematical approximation. On to Section 5, Active Dreaming. This is super cool. Basically, how do we get an agent to extract general rules from its own specific failures? To stop these agents from learning totally the wrong lessons, researchers developed a process called active dreaming. And get this, it actually mimics how a mammalian hippocampus consolidates memories while we sleep. Basically, during an offline sleep phase, the AI simulates hypothetical, counterfactual scenarios. It takes its newly generated rules and tests them out in these synthetic environments, just to verify they actually solve the underlying problem. This ensures the AI only commits the most highly reliable rules to its long-term semantic memory. So picture this pipeline. During the wake phase, raw episodic failures happen. Normal stuff. But then, during the sleep phase, the system fires up a clustering algorithm, like dbScan, which essentially just groups together data points that are packed closely together to find hidden patterns in those similar errors. Next, an LLM steps in to extract a generalized rule and performs the absolute most critical step, counterfactual verification. The system actually generates edge cases to rigorously test the new rule. If it passes the acceptance threshold, boom, the agent wakes up smarter and executes its tasks flawlessly the next day. And the data-driven proof backing up this offline consolidation is pretty staggering. In really rigorous stress tests involving task interference, an agent utilizing active dreaming maintained a massive 95% retention rate of its learned rules. I mean, wow. By effectively separating raw episodes from consolidated knowledge, it completely bypassed the catastrophic forgetting that normally plagues baseline models. It's a total game changer. Which brings us to our final stop, Section 6, Strategic Forgetting. We're facing a bit of a paradox here, folks. Boundless memory is actually a massive liability for an AI agent. Think about it. If you store absolutely everything forever, retrieval speed plummets, and your costs, they just skyrocket. We literally have to implement selective forgetting. To keep the vector database from just becoming this messy landfill of useless data, we can use something called the RFI formula to evaluate memories. R is for recency, meaning older information naturally experiences temporal decay and fades away. I is for relevance, measuring the semantic similarity to whatever the current query is. And F is for frequency, which tracks how often a memory is actually accessed or proven useful. The entries that score low on this RFI scale, they are simply pruned away. This actually directly mirrors the Ebbinghaus forgetting curve in human psychology. When AI memories are accessed repeatedly, they get heavily reinforced, meaning their decay rate is actually lowered over time. The system naturally learns, oh hey, this information is actually valuable. Meanwhile, all those unused, trivial little details just naturally decay and are strategically forgotten over time. This keeps the whole database incredibly lean, incredibly fast, and very cost-effective. Which really leaves us with a final, somewhat provocative thought about the future of AI architectures. Something for you to ponder long after this explainer wraps up. You know, we spend so much engineering effort trying to make these agents remember absolutely everything. But as they scale into lifelong companions and fully autonomous workers, it turns out that their true capability, well, it might just rely on mastering the fine art of forgetting. Thanks so much for joining me on this deep dive into agentic memory.